Namaste and welcome to yet another lecture on linear algebra through geometry. In the last lecture we looked at Ax is equal to b and we said that what is it to say that I cannot find a solution for Ax equal to b. And we figured out that if I am not able to find out a solution to Ax equal to b, we said that b is not in the column space of A. And in that case we said that if you have, let us say you are given a system A and you want to find out what is the is the condition that B has to satisfy in order to have a solution to Ax equal to b. We figured out that and we said that look, this is what the consistency condition is, and the consistency condition was the vector b that we had, the dot product of the vector b with the solution to the homogeneous system of equation A transpose y is equal to 0. If the dot product is 0, then we said that is basically b dot y is equal to 0 is the consistency condition, where y is basically from the null space of A transpose, right. Let us just look at what it is to say b dot y is equal to 0. Let us look at it geometrically and then go ahead figuring out what happens when I do not have that condition to be satisfied. Geometrically let us just figure that out how it is going to be. So yeah, let us go ahead. Recall that we had this figure. Recall the orientation between, we said that range of A transpose is orthogonal to null space of A in Rn, and range of A is basically orthogonal to Na transpose in Rm, where for any matrix A this is what we had, right. Now let us look at things geometrically and again try to understand the consistency condition business. So what we had this Rn and we had this Rm, and remember we had in fact we had told that the figure that we drew there was the cover page figure of the Introduction to Linear Algebra textbook by Gilbert Strang, Professor Gilbert Strang. So we have this is basically the null space of A and this is the range of A transpose. Then we had this which was basically the range of A and null space of A transpose, this was null space of A transpose, and this is basically the range of A. If you recall, in the last lecture we said that for the consistency condition for B to satisfy was basically saying that you cannot have any B vector in Rm which can be expressed as Ax. Instead, if I take this to be my vector x, what A does is it takes this A and then it transforms to a vector which is in the row space of A, which is which is in the column space of A, which is basically my B vector, right. It takes any vector Ax basically is any vector B in the column space of A. Now what did we tell in the last class, in the last lecture? We said that B dot the null space, suppose if y is a vector in the null space, we said that b dot y should be equal to 0, and the interpretation we already had, we will be able to find scalars x1 x2 xn such that B can be written as linear combination of A, the columns of A. It simply meant B must be here, B must be an element of the range of A, and the moment you know that B dot y is equal to 0, you already know that B is in the range of A. That is what it means. The consistency condition saying B dot y is equal to 0 simply says that B must be in the range of A. Whenever B is in the range of A, B dot the y the corresponding to the solutions of homogeneous system of equation A transpose y is equal to 0, that will be 0. This is exactly what manifested as your condition, consistency condition in the last lecture that we saw. So the question now we have is, suppose I do not have this B to be in the column space of A. So let us look at this. Suppose we do not have the B, suppose B is not in the column space of A. Now what does that mean? You cannot find x1, x2, xn, you cannot find scalars. This means no scalars x1, x2, xn exist such that B is equal to x1 a1 plus etc plus xn an, where ai is ith column of the matrix A. What do we do? In that case, we try to look at the representative of the B vector in the column space of A. Yeah, we want to look at the representative of the B vector in the column space of A. What is that vector which best approximates the B vector in the column space of A? That is exactly what we are looking for. So let us look at this. Say for example, I have, let us say this to be my column space of A. Let us assume that I have this, and this is my x1, x2, x3 axis, right. Let us take this x1, x2, x3 axis. I have this to be my column space of A, and I have this vector B which is here. That is exactly what we said. So now B does not belong to the column space of A. Now what does that mean? If you look at it in the previous figure, B is somewhere here and it is not in this. The B vector that we are looking for is basically here, it is an element of Rm but not an element of Ra. Yeah, so what we say, B is an element, because we know that B is an M component vector, B is in Rm but B does not belong to column space of A. Now what do we do? It is interesting that we have studied this before, a couple of modules before, where we said if you are not able to find if you are not able to express B as a linear combination of certain set of vectors, what you do is you project that B vector onto the geometry, onto the onto the span of the set of vectors that we have. Basically that will be a vector space. You have this vector space here, it is going to be a plane passing through the origin. So what you do is you project that B, you do project that B, so that is going to be the, let us take this is basically projection of B onto the column space of A. Now the moment you project B to the column space of A, that fellow exists in the column space of A, which means the orthogonal projection of B is the best representative of the vector B in the column space of A. The orthogonal projection of B onto the column space of A is the best representative of the vector B in the column space of A. This is something which we have studied already, right, and we also figured out that you can actually find out what is the best optimal solution and all. We will just do that quickly, and before we will do this and then we look at the idea of certain projection matrices and stuff. So that is the agenda of this class. So we will look at this, we will try to find out what we call as the best optimal solution, because you whatever x scalars that you put are not going to reach B at all. Therefore what I do, I project my B onto the column space of A. right. So what we want is we are going to project B onto the column space of A such that what we want is this. So the question is, so the following holds. So since B does not belong to the column space of A, we would like to approximate B in the column space of A. That is, we want to find that vector B star which best approximates B in the column space of A. Now what do we mean by this? When we say we want to find out the best approximate of B in the column space of A, what are we trying to say? That means the difference between the vector B and the approximate that you have, the squared error must be as small as possible. That is what we call as the idea of least square solution. So we want the difference between the original B vector and the representative of B vector in the column space of A, the squared difference between these two to be minimum. That means we want to find out that x value which is going to give me that B star value in the column space of A such that the difference between the original B and the B star that you have, the squared difference, is going to be minimum. If the vector B is already there in the column space, there is nothing that you need to do because B itself is getting approximated in the column space, therefore the error is going to be 0. But in this case, because it is not there in the column space, the error is not 0, therefore you want to find out that vector which gets approximated in the column space of A with minimum error, with least error. That is least error in the squared sense. That is exactly what we are looking at. Yeah. So let us look at this. So we want to look this. So note that for whatever x we take, for whatever x we have, B minus Ax will never be 0. It will never be 0, sorry, not the vector, it will never be 0. The length of B minus Ax will never be 0. Why? Because you cannot find scalars, because no scalar, no x1, x2, no x1, x2, xn exists such that Ax is equal to B, right. So what do we want? We want to look at this. So we want to make, let us write this. So we want to make B minus Ax as small as possible. As small as possible. That means, if, what do we mean by that? We say that if we can find let us say unique vector x star that minimizes the error, that minimizes the length or the error, the length of b minus ax we call x star to be the best optimal solution to ax equal to b in the sense of least squares. In the sense of least squares, right. So, what we want is basically we want to find out that x star which minimizes the length of b minus ax. Now, let us look at this again. We had this, assume that this is the column space of A and assume that this is the vector B and assume that okay, this is the vector Ax star. Now, what we want this is the vector basically which is B minus A x star, is that right? That is the vector B minus A x star. So, what we see B minus A x star B minus A x star is okay, let us do this, let us take this B minus Ax, the length of B minus Ax is the smallest when Ax, we will call this as Ax star, when Ax star is the orthogonal projection. We have already seen the minimal length and orthogonal projection and stuff. We said as the orthogonal projection of B onto the column space of A. Now, what does that mean? That means the following: B minus Ax star is orthogonal to the column space of A. Now, this is clear. We have understood that B minus Ax star is going to be the orthogonal. I mean, is basically orthogonal to the column space of A. What is it to say orthogonal to column space of A? Any vector in the column space of A can be expressed as A into, let us say, some u. For u vector in Rn, I can write AU to be the vector which is there in the column space of A. Is that correct? So, we can do that. So, what we are going to do is we are going to look at this. So, we want is ortho. So, we want B minus A x star to be orthogonal to every vector in the column space of A, every vector in the column space of A. Now what we do is, any vector in the column space of A can be represented as any vector in the column space of A is equal to AY. It can be expressed as AY for, let us say, every y in Rn. Therefore, what we want? We want B minus AX star dot AY to be equal to 0, right. This is basically the set of vectors in the column space of A, and this is basically the projection of the B vector, the orthogonal projection of the B vector onto the column space of A, and therefore it will be orthogonal to every vector in the column space of A. That is fine now, right. So what do we have? We basically have AY the whole transpose into B minus AX star is equal to 0, which is nothing but Y transpose A transpose into B minus AX star is equal to 0. What do we have? We have Y transpose into A transpose B minus A transpose A X star is equal to 0. Now there are two things that happen here. Y is a vector and A transpose B minus A transpose AX the whole star is equal to 0. That A transpose B minus A transpose AX star, that is another vector. So this is a vector and this guy is another vector. So the dot product of these two vectors is 0. Definitely Y is not the 0 vector for the simple reason that we are looking at all possible Y, therefore Y can be any vector in Rn, then therefore AY will be in the column space of A. So therefore Y vector cannot be 0 vector. Therefore what we do, we say that so let us look at this. So what we do is, okay, for every vector Y in Rn, every Y in Rn. Now what is the only vector which is orthogonal to every other vector? That is basically the 0 vector. Therefore this implies A transpose B. So let us write this. Since the only vector which is orthogonal to every vector in Rn to every vector in Rn is the 0 vector, we have A transpose B minus A transpose A X star to be equal to the 0 vector, right, which implies we have A transpose A X star is equal to A transpose B, and you look at this A transpose A, if A is an element of Rm by n, A transpose will be an element of Rn by m. So A transpose A will be a square matrix of dimension n by n, of dimension n by n. So let us look at this. Suppose the columns of A are all linearly independent, that simply means the rank of A is n, A transpose A will also have a rank n and A transpose A will be invertible. Right. The columns of A are all linearly independent, therefore the rank of A will be n and therefore A transpose A will be invertible, which implies my x star is going to be A transpose A the whole inverse A transpose B, and that is what we call as the best optimal solution to Ax equal to B when Ax equal to B does not have a solution. Is that okay? So let us write that. So x star is equal to A transpose A the whole inverse A transpose B is the best optimal solution to Ax equal to B. And this is basically my linearly and this is basically my solution to the system of equations in the least squared sense, right. And most of the textbooks they use this notation x dagger and then say this is basically A transpose A the whole inverse A transpose B, we say this is nothing but x dagger. Right. So this is basically the best optimal solution that we have. Now what is interesting again is basically let us look at this. So we, if you want to look at this, so what is it that we had? We wanted to solve Ax equal to B, but no solution for A, but if B is not an element of column space of A, no solution exists. Therefore, we solve for Ax dagger which is equal to let us say some B star, where B star is basically what? Where B star is the projection of B, in fact orthogonal projection of B onto the column space of A. Right. We are trying to solve Ax star is equal to B star. So let us look at this quickly. So we had x dagger to be of the form A transpose A the whole inverse A transpose B. Now just focus on this part. Suppose we have A which is an invertible matrix, then given Ax is equal to B, we can write x is equal to, we get x is equal to A inverse B. Let me call this as equation 1 and let me call this as equation 2. If you compare equation 1 and equation 2, this A transpose A, the whole inverse A transpose, seem to do something similar to what A inverse does when A is an invertible matrix. It is something similar to that, like it here also on the left hand side we have X dagger, on the right hand side we have B, which is pre multiplied by A transpose A, the whole inverse into A transpose, whereas whenever you have an invertible matrix A, we have X is equal to A inverse B. So what do we get from here? So if A is a rectangular matrix, then we say that A transpose A, the whole inverse A transpose, we are going to call this by a name, this is basically called the pseudo inverse of the matrix A, pseudo inverse of the matrix A. It is not the true inverse because inverse is not defined for rectangular matrices, therefore what we have is basically a pseudo inverse, right. Okay. Now let us look at this. Let us just take this again. So we had X dagger is equal to A transpose A, the whole inverse A transpose B, yeah. So let us look at what is AX dagger. What is AX dagger? AX dagger, look at AX dagger. AX dagger is basically A into A transpose A, the whole inverse A transpose B, is that right? AX dagger is basically A into A transpose A, the whole inverse A transpose B, this is what we have. But what is AX dagger geometrically? Geometrically this corresponds to the projection of B onto the column space of A. Onto the column space of A, which means this matrix that I have A into A transpose A, the whole inverse into A transpose, that seems to be doing the, okay, let me write this, that seems to be doing the operation of projection of B. It is basically this entire thing that you have here, A into A transpose A, the whole inverse into A transpose, seems to be the matrix which does the projection of B onto the column space of A, yeah. AX dagger is basically the projection of, it basically looks at the projection of B on the column space of A. If you look at the figure correctly, we see this is basically B minus AX dagger, let me put that. So B minus AX dagger, this is AX dagger. So what is this? AX dagger is the projection. So AX dagger, let us do this, we have written here AX star is the orthogonal projection of B onto the column space of A. So let us write here AX dagger is the projection of B onto the column space of A, therefore the matrix A into A transpose A, the whole inverse A transpose, is the matrix that projects, the vector that projects every B onto the column space of A. Onto the column space of A, right. Oh, but how do you know that the matrix is actually a projection matrix, right? So the question that we have is, how do we know? Conceptually we can see that it basically does the projection. So, how do we prove that? A into A transpose A, the whole inverse A transpose is actually a projection matrix. And that brings us to the question of what is a projection matrix. So, what is a projection matrix? And what are the properties of projection matrices? What are the properties of a projection matrix and so on. So, we have a lot of questions to answer. So, in this module, in this lecture, what we saw was if the vector B was not in the column space of A, that means no way you can find scalars to express B as a linear combinations of the columns of A. What we did was in order to find out what is called as a best optimal solution, we found a representative of the B vector in the column space of A, and this representative, the best representative, was basically the orthogonal projection of the B vector onto the column space of A. The moment you projected the vector B onto the column space of A, this projected vector is already there in the column space of A, therefore we can find scalars with which we can write this projected vector as the vector that is available as the projection, the representative vector of B, we can write that as a linear combination of the columns of A. Now, having done that, we found a best optimal solution. Suppose that the matrix was of full rank. By full rank we mean the rank of the matrix is equal to the number of columns. If that happens, then we figured out the best optimal solution was basically A transpose A, the whole inverse A transpose B, and we figured out we were not solving the problem Ax equal to B, instead we were solving the problem Ax star or Ax dagger is equal to the projection of B onto the column space of A, and we figured out that the matrix A into A transpose A, the whole inverse into A transpose, basically projects every vector B onto the column space of A. Now, the moment we say it is a projection matrix, we first of all need to know what is a projection matrix. What is a projection matrix? What are the properties of a projection matrix? And then we will come back and see whether this matrix that we had, which was basically A into A transpose A, the whole inverse into A transpose, whether that is a projection matrix. So, in the next lecture what we will do is we will look at what is a projection matrix, how do we get projection matrices, and what are the properties that a projection matrix has to satisfy, and then look at whether whatever that we have written as a projection matrix is indeed a projection matrix, whether it actually obeys the properties that we list, followed by we will spend some more time on the pseudo inverse. We also discussed about pseudo inverse in this class, where we said A transpose A, the whole inverse A transpose looks like in some way it mimics the inverse of a square matrix, where if you have Ax is equal to B and A is invertible, we said X is equal to A inverse B, and here what we had is we had Ax dagger is equal to this projection into B, and we said X dagger is equal to A transpose A, the whole inverse A transpose into B. So, the A transpose A, the whole inverse into A transpose looks like it mimics that, or it looks like an inverse, but A being a rectangular matrix, we cannot do the actual inverse because inverse is not defined. So, what we did is we call this as the pseudo inverse. So, in the next class what we are going to do is we are going to look at the properties of a projection matrix, followed by, in subsequent class we will look at the properties of pseudo inverse, and we will also look at pseudo inverses of inverse of certain special matrices. We will discuss what they are as we progress. So, that will be the agenda for the next couple of classes of this module. Namaste.